roughly steel makes up about 3% of the economy. If you look at the GDP, the steel sector is somewhere around between 3 and 4%. And as we go up in value of steel addition, the thought process is that our consumption is going to go up and steel is going to become even a larger part of the economy. But unfortunately, because it is so energy intensive and you use coal and iron ore based process, our emissions are about 10%, between 10 and 12% of the total emissions. So obviously we have, villain typed across our forehead, as far as emissions go. So we have our work cut out, and we really need to invest in technologies that are emerging. And today what I'm going to do is I'm going to present just the use of hydrogen and how using hydrogen is going to reduce our carbon footprint. We'll start off very small. Right now, it's a TRL-7 based technology, let's say. The electrolyzer part is a TRL-10. We have experience running electrolyzers, so we can get the green hydrogen. We have solar and wind capability, so it'll be green. It's not gray or purple or any other color. But how do we inject it in an operating furnace is what we are going to learn over the next few years. So there is a group, a global group called World Steel Association, which represents about 92 steel companies across the world. And what they do is they collect all these statistics. And if you look at this table, what I've represented is a study till about 2023, and it was published like last November. So it is as good as it gets as far as the sustainability metrics goes. So you can imagine number 1 and number 2, there is a reason why those are number 1 and number 2. It's the greenhouse gas aspect and the energy aspect. And towards a large, I would say a factor, both of them are interlinked. So you reduce one, you reduce the other one. So essentially what we are looking at is that number on the very right. Let me see if this one can show. Yeah, so this is the number that we are looking at, 1.92 tons of CO2 per ton of crude steel cast. And then, of course, the energy is about 21. So you can see the numbers are hovering around 1.9. And the goal is to kind of get it down to, if you look at it at a 1.5 degrees Celsius rise in temperature, you have to really get it down to about a 0.1. That's what the target is. When you say net zero, that is how far we have to go. And this is the global average by process. So if you look at it, there are 3 distinct processes of making steel. One is the blast furnace BOF, which is the most popular one in India, just because we have iron ore, abundance of iron ore. But it uses coal to reduce iron ore, so it's more intensive. So you can look at it, if we kind of consider it's at about a 2.3, whereas what are we doing at JSW Steel? So progressively over the years, we have been able to reduce our specific energy consumption to about 5.65. This is in gigacal instead of gigajoules. I didn't have the time to convert it to joules and present it. And then GHG emissions, we have reached about a 2.4 number. Now, what we do is we get financing in the open market. So we have a target of getting it down to 1.95 by 2030 because we have gotten financing. So how are we going to do it? So there is a stage 1, which is basically trying to get down to 1.95. So these are the essential basic steps. And World Steel Association always mentions these things as what is called a step up. Means just improving process efficiency, recovering waste heat, and things like that. And if we look at our latest blast furnaces, we are very close to 2 by following all these practices. So the larger the furnaces, you can deploy better technologies. I've got numbers that I will show you how we can go ahead and kind of reduce it even further. Now, if you look at it beyond 2030 to 2050, some of these technologies are still at TRL 7-8 level. We think they are going to be deployed. There are going to be policy prescriptions, market drivers, which will kind of demand that more and more of this green steel is produced. So there will be incentive to use some of these technologies on a large scale. And what we are doing is, as a company, we are just starting off on this one. We'll go through the details on how we are doing hydrogen. So that was the hydrogen use case. Simply put, I have to give you a little bit of background. Where do we make steel? So if you look at it, our biggest and the shiniest steel plant is in Vijayanagar, which happens to be in this state. It's about 330 kilometers from here. And this is the single largest location in India because it produces almost 10%. This year, it will produce more than 10% of India's steel. So it's a very large facility, 10,000 acres, sprawling facility, and it is located right in the Ballari iron ore rich area. So obviously, if we can decarbonize Vijayanagar, it will go a long ways in decarbonizing JSW Steel. And how is Vijayanagar history? If you look at it, we started off very small in 1999, 0.8 million ton, with a process called Corex. Then we started putting in blast furnaces. Then we have DRI plants also when we went from 10 to 12. So at one location, we have both the blast furnace as well as DRI. So it makes sense to start using the hydrogen here because that way we can scale up much faster. So this is the 5 blast furnaces that we have. Going from the latest one, what we call is the blast furnace number 5. It was just commissioned about 3 months back. So one of the things that I want to note is if you look at it, the top pressure. So it's like a container. So if you want hydrogen to be injected in there and react, and you have to give it time, you have to build up pressure. So that's why what we are saying is the top pressure is probably going to be the biggest driver. So if we look at it, these are the older furnaces, smaller furnaces. As we get bigger and newer technologies like top recovery turbines and all those things come up. So we are able to operate these furnaces at a much higher pressures. So right now we are operating it at 2.6 bar. We want to get up to 3 bar. Now modern DRI can go even double, up to 6 bar pressure. So what you need is a pressurized reactor in order for hydrogen to be more effective. So that's why we are planning on injecting hydrogen in this furnace. What are we doing? We have this PERIC supplied alkaline electrolyzers. We already have experience running this for the last, I would say, 15 years. So we're just scaling up. So we'll build a 25 megawatt electrolyzer, which will consist of 4 electrolyzers, 33 kV, and a total of 5,000 normal meter cube per hour of hydrogen is going to be generated. So this is already under construction. It's going to be commissioned by May. So we'll have this hydrogen available, and this is all green, means it is going to be supplied through solar and wind. So a lot of interesting activity taking place in Vijayanagar. And in fact, if you look at it, it'll probably be one of the first continuous hydrogen supply at any steel plant location in the world. Rough idea, just a Google map just to show you. It takes about 3 kilometer long worth of pipe, to kind of bring so we are kind of working on the kinds of steel that we need to use, with a whole lot of engineering going on. So we're going to do it in 2 stages. The first one is 25 megawatt, which we are starting right away in March, April. And then we're going to add another 75 megawatt. So 5,000 plus 15,000. So we'll be at a level where we think we can make an impact and study the effect. And on an operating blast furnace where we continuously inject so that we have an operational experience. So far worldwide, nobody has done it more than, let's say, a week, or a couple of weeks at a time. So we are taking the leap of faith that this works based on other people's experience, and now we need to run it continuously in the furnace and see the operating conditions. So what does hydrogen do? One of the unfortunate sides of the hydrogen thing is as you inject more and more, the adiabatic flame temperature keeps going down because the reaction is endothermic. So you have to compensate it with oxygen enrichment. So then what happens is that uptake temperature also starts dropping. So there is a limit to which how much hydrogen you can inject. You cannot inject 1 to 1 and kind of say, I can remove all the coal and inject hydrogen. So safe limit, people say, without having to preheat hydrogen, you can go up to 20. We think we can start off with 3, run it for a year. Then if we need more, we get some more money, build more electrolyzers, and start slowly replacing. So this is our plan. Just a rough sketch. Initially we'll start off with 5,000 normal meter cube per hour, then we are going to ramp it up to 20,000. One of the interesting thing technology-wise is how do you inject it? So these are the tuyers. We have 42 of them. So one of them is to kind of use a lance, but this restricts it because this is a very easy. You can inject a small one. But then you can really have a properly designed lance which goes inside so that you have oxygen, you have carbonaceous material, we call pulverized coal injection. You have then with that hydrogen so that the whole mixture is swirled. And there are a lot of technologies coming up with this thing that you can pulsate these things called SIP. Means all these things for the flame to penetrate deeper and kind of shatter all the material in its way, the better thing to do is to pulsation. Now Germany is working on to kind of inject hydrogen also pulsating in ThyssenKrupp, so they are starting experimenting. So all these, it's an amalgamation of our different technologies that are going to come together over the next 2 to 3 years. So this is a cutaway section of the, you can see all those 42 tuyers around the furnace if you look at it from the top. So our idea is to kind of start initially doing 1 in 3 so that you are injecting it at different or not through all of them. And the idea here is to kind of predict the adiabatic flame temperature. Now we have the ability to measure the flame temperature through probes, optical parameters at each injection point. So we can measure if you inject 1%, 2%, 3%, what is the drop in adiabatic flame temperature. So from a research perspective, that's what is the first step, trying to prove that this equation works. This is a simulation that we have done. Obviously, one of the drawbacks is when you inject a gas inside a cylinder, it tries to stay close to the wall. So you can see more of the reducibility, reduction of the iron ore takes place here. So the challenge is how do you avoid channeling? So that when you are injecting this hydrogen, and it's not a big problem at what levels we are injecting, but if we start injecting in a significant way, 10 kgs, 15 kgs, 20 kgs, we have to figure out how to avoid this channeling. So this is some serious R&D work that requires injecting more and more hydrogen. Coming to the summary slide, this is essentially summarizes the whole thing. Right now, if you look at it, our CO2 emission with the current coke rate is about 960 kgs from a blast furnace 5. So when we approach this one emission at the first phase 1, we'll be able to reduce it, roughly about 20. It's a very small. All I say is research is very difficult when you're starting on a new technology, but one step builds up to another step. So concluding, I think, is just to give you a flavor. We're getting technologies that are approaching commercial scale, but scaling up is going to need a lot of support from the government as well as the market, and we are looking forward to implementing this project in Vijayanagar this year. Thank you. Any questions?
Yeah, hi, sir. I'll keep this short. So JSW has like a CRGO steel production project in collaboration with another firm. Which
How do you know that? That's supposed to be a company secret, huh?
So as far as I know, it's a polluting process, which is why India has been importing so far. Since it's like the first one in India, how does JSW plan to tackle it? Any?
Say that again, the CRGO?
The production is like extremely polluting. As far as I know, it's one of the reasons why we have been importing it from other countries. So.
No, I would say the product itself, in the final stages of production, yes, it will be a little bit more carbon intensive because it's a very, very sophisticated way of producing it. But if you look at just the savings, by using a very high-grade CRGO, your transmission losses that you're going to save, the previous gentleman said it's going to go to a 800 kilovolt DC line, because your generation is further away. So there's going to be a lot of transformers, heavy-duty transformers that are needed. So we have done a cost calculation, LCA, life cycle analysis, and we are probably going to, as soon as we start production, we're going to show through EPD that the savings that you get by using a higher quality CRGO, it will overwhelmingly offset the carbon footprint that is involved in the manufacturing of it. So I understand that, yeah, it's going to be a little bit more energy intensive than for, let's say, mild steel, but if you use mild steel in a transformer, you're going to lose a lot of, conversion losses. So the grades that we are talking with our technology partner, JFE, we are partnering with JFE, these things have a loss that will reduce, let's say, 3% transmission losses right now. These will reduce to 0.3% if you use this kind of steel. So it's a game changer. It's a step up in efficiency.
Thank you.
Good question, though. We have to give it more thought. Okay. Thank you very much.